Alright, welcome back everybody. We're going to begin this video with another example of finding a potential function given a conservative vector field and then using the fundamental theorem of line integrals to evaluate the integral. So here we want to find this line integral of f where f is 1/2 xy 1/4 x squared over a parabola from 0, 0 to 1, 1. The first thing we should check is see if f is conservative. If f isn't conservative, we could still calculate this line integral. We're just going to have to find a parameterization and go through it the way we did in section 16.2. So this vector field is defined on all of R2, and that's open and simply connected. These partial derivatives are continuous and they equal each other. So yes, this is a conservative vector field. Just to remind you, we took the partial derivative of the first component with respect to y and the partial derivative of the second component with respect to x. If those two are equal and all the assumptions are fulfilled, we have a conservative vector field. Our next step is to find the potential function, and this is where most of the work is going to be. I'm going to use method 2 that we discussed in the last video to find out what the potential function is, lowercase f, whose gradient is given by this vector field. So I'm going to start by integrating this first component, integrate p with respect to x. Remember, p is the partial derivative of the potential function with respect to x, so if I integrate it with respect to x, I should recover my potential function. So I integrate 1/2 xy, I get 1/4 x squared y plus a function of y, because I might be missing terms without x's. And I'm just going to call that function g of y. Now I take a partial derivative of what I just found with respect to y, and that should be the same as the second component of my vector field, because this is going to be the gradient of lowercase f. So I take a partial derivative with respect to y that gives me 1/4 x squared plus g prime. Since this is just a function of y, I set that equal to the second component of f, which is 1/4 x squared, and then I solve for g prime of y. But this shows me that g prime of y is 0. If I cancel out this 1/4 x squared, all I'm left with is g prime. Well, if the derivative of this function is 0, that means the function itself was a constant. So g of y is just an arbitrary constant, and here is my potential function. F is 1/4 x squared y plus k, some arbitrary constant. I can check by taking the gradient, and this is relatively simple for this example. I take a partial derivative with respect to x, I'm going to get 1/2 xy. I take a partial derivative with respect to y, I get 1/4 x squared. So this is indeed the gradient of this function. Okay, so now I've found my potential function. I need to find the endpoints of my curve. Well, they're given to me. It says the curve goes from 0, 0 to 1, 1. So I'm starting at 0, 0, I'm going to 1, 1. I'm ready to evaluate this integral. The integral of f over this curve is lowercase f, my potential function at the endpoint, minus my potential function at the initial point. So if I plug in 1, 1, I get 1/4 1 squared times 1 squared times 1. I plug in 0, 0, I subtract 1/4 times 0 times 0, the answer is 1/4. And I don't need to consider this constant at all, it would cancel out anyway. And that's the answer. So now I have a question before we move on. Where in this problem did I use the fact that the curve is a parabola? And think about that for a minute. I didn't use the fact that we were integrating over a parabola at all. All I used were these endpoints. I didn't use the curve itself anywhere. I didn't parameterize it. There was no r of t or anything. So we found the answer without using the parabola. We just used the endpoints. So does the curve matter? And this leads into our next topic, independence of path. If f is a continuous vector field, and the integral of f over a curve is the same for every piecewise smooth curve sharing the same endpoints, we call that integral independent of path. So as an example, let's suppose that I just want to integrate starting at this point and at that point. If my integral is independent of path, I can integrate over this curve, that's fine. I'd get the same answer if I integrated over that curve. It doesn't have to be smooth, it could be piecewise smooth, so I could integrate over these two line segments. As long as I start here and end here, I'll get the same answer. If I take this strange curve where I'm going down for the first piece, the second piece kind of looks like a circle, the third piece is going around like this. Or I could use even any other smooth curve. It could go off the page. It could go over here, go all the way up here and around and crazy, as long as it's piecewise smooth and it ends there. I would get the same answer if my integral is independent of path. And so this is really nice. How do we know which kinds of vector fields will give us integrals that are independent of path, so we don't have to worry about the curves anymore? We can just worry about the endpoints. If f is conservative and continuous on the curve, then the integral is independent of path. So if we have a conservative vector field, the curve doesn't matter. All we need are the endpoints of the curve. Now, what if we have a closed curve? If I have a closed curve, something like this here, where I'm starting at this point and going around and stopping at this point, if my vector field is independent of path, well, the ending point and the starting point are the same. So that integral is going to be 0, right? If it's a gradient, it's 0. If we integrate over any closed curve in the domain where the vector field is conservative, then that integral is 0. So if you have an integral that's independent of path and you're integrating over a closed curve, the answer will always be 0. Now, if you look back in the notes for section 16.2, there was an integral that we took, one of the examples that ended up being 0, and if you go back and look at that example, you'll see that what we're actually doing is integrating a conservative vector field over a circle of radius 3. Now, it takes some work to show that what we have is the integral of a conservative vector field, but we do. And so if we had known that ahead of time, we wouldn't have had to do all that work. We parameterized the circle and plugged things in and worked it out the old-fashioned way. We would have known ahead of time that the answer was 0. But oh well, we know it now. There's one last result. So we know if it's a conservative vector field, that our integral is independent of path. Are there other integrals that might be independent of path if we don't have a conservative vector field? So this theorem says that we have some vector field that's continuous on an open connected region. If the integral of this vector field is independent of path inside this region, then f is a conservative vector field. In fact, this is how your textbook defines conservative vector fields. They're vector fields that are independent of path. So if it's conservative and it satisfies all of the hypotheses we've talked about before, then the integral is independent of path. If we have an integral that's independent of path of a vector field, then that vector field has to be conservative. They're equivalent statements. So only conservative vector fields are independent of path. So we're only talking about gradient fields, right? Because conservative vector fields are gradient fields. Okay, now to finish up this lesson and finish up this video, I want to look at an example using a three-dimensional vector field. The two examples that we've done, the one at the end of the last video, the one at the beginning of this video, they were both two-dimensional vector fields. To finish this up, we'll do a three-dimensional vector field and show you how things get more complicated in 3 dimensions. Okay, so now find this integral of f dot dr. F is three-dimensional. It's yz plus 2x, xz minus 3y squared, xy plus 1 over z, where c is any curve from 0, 0, 1 to 1, 2e squared that lies above the xy plane. Now, why are we saying this has to lie above the xy plane? Well, in order for this to be conservative, right, we have to check those 3 conditions, and we have to be in a region that's open and simply connected. You'll see that this last component function isn't defined when z equals 0 in the xy plane. So since both of these points are above the xy plane, we have to stay above the xy plane. If we cross the xy plane, then this function is not going to be defined. So the xy plane cannot be part of our open simply connected region. So is f conservative? The region that we're going to consider is just the region of space above the xy plane. So anything where z is positive, not including the xy plane, and it's simply connected. Now we have 3 conditions to check. Since it's a three-dimensional vector field, I take a partial derivative of the first component with respect to y. that has to be equal to a partial derivative of the second component with respect to x. Well, they're both z. I take a partial derivative of the first component with respect to z, that has to be equal to a partial derivative of the last component with respect to x, they're both y. And then I take a partial derivative of the second component with respect to z, has to be equal to the partial derivative of the last component with respect to y, they're both x. So those three conditions do hold. It's a conservative vector field. Now I need to find the potential function. Again, I'm going to use method 2. It's going to be a little more involved this time, because now I have three pieces of information. I have three components in my vector field, and eventually I'm going to end up using all three of these pieces of information. So first, let's just write what we know. The first component, yz plus 2x, is equal to the partial derivative of our potential function with respect to x. The second component, xz minus 3y squared, has to be the partial derivative of our potential function with respect to y. And the third component, xy plus 1 over z, has to be the partial derivative of our potential function with respect to z, because we're saying that this vector field is a gradient of some potential function. And that's what it means to be a gradient. It's the vector of partial derivatives. So I'm just going to pick one of these and integrate to recover f. So if I pick the first one, I need to integrate with respect to x to get f back, and that's what I'm going to do. So I integrate p dx, that's integrating yz plus 2x with respect to x. That gives me xyz plus x squared, plus I might be missing terms that have y's and z's. So if I take a partial derivative with respect to x, it gets rid of any term that doesn't have an x. But now I have more options since I have more variables. I could have terms that only have y's, terms that only have z's, terms that have y's and z's together, and constants. So I'm possibly missing a function of two variables. Whereas in a two-dimensional case, at this point, I only had a function of one variable. So now I proceed as I did before. I'm going to take a partial derivative of my potential function and set it equal to another component. I have two choices. I could take a partial derivative with respect to y or with respect to z, but let's just take a partial derivative with respect to y. That's going to give me f, the partial derivative of f with respect to y, because this expression is f. This is my potential function. So I'm going to take this partial derivative, set it equal to q. Right? The partial derivative of f with respect to y equals q. So then I take a derivative with respect to y. I'm going to get xz. This x squared is going to drop out. And now, since this is a multivariable function, it's a function of two variables, I have to take a partial derivative of that function. I can't say g prime anymore. G prime doesn't make any sense. And I set that equal to q, which is xz minus 3y squared. And now I need to solve for the partial derivative and eventually recover g. So I can get rid of xz and xz. So that means the partial derivative of this g function with respect to y is equal to negative 3y squared. I want to recover g now, so I integrate with respect to y. If I integrate both sides with respect to y, here I just get g. I integrate negative 3y squared to get negative y cubed plus h of z. I might be missing a function of z. Now, why aren't there any x's here? Because all of the x's have already been taken care of in this step. This step recovers any term that could possibly have an x in it. Now what I'm doing in this step is recovering any term that could possibly have a y in it. So now all that I could be missing are terms with z's or constants. Okay, so now I've solved for this function of two variables. I'm left with this one term plus a function of one variable. I need to go back to my potential function f and say, okay, now I have a better representation of f, better than this, because I can replace g of yz with negative y cubed plus h of z, and that's exactly what I do. So now this is my potential function, the terms that I had before, xyz plus x squared, and now I have minus y cubed plus some function of z. Well, the information I haven't used yet is this third component. I know this third component of my vector field is the partial derivative of f with respect to z. So I'm going to take this potential function, take a partial derivative with respect to z, set it equal to that third component. When I do that, I'm I'm going to get xy coming from this term. These two terms drop out, and I'm left with h prime of z, because now this is a function of one variable, so h prime makes sense. And that's equal to the third component, which was xy plus 1 over z. Now I solve for this h function. H prime equals 1 over z. I integrate with respect to z to recover h. If I integrate 1 over z, I get the natural log of the absolute value of z plus k. Now, since my region where I'm looking is above the xy plane, all of these z's are going to be positive anyway, so I don't really need these absolute values. But it's just best practice to put those. So I'll leave those absolute values there. Now that I know what h is, I can plug it back in, and finally I have my potential function. My potential is f of xyz plus x squared minus y cubed plus the natural log of the absolute value of z plus k, an arbitrary constant. I can check my work by taking the gradient of this potential function. I take a partial derivative with respect to x. I'm going to get yz plus 2x coming from these two terms. These three drop out. I take a partial derivative with respect to y. I'm going to get xz coming from this term. X squared drops out. I get negative 3y squared from this term. These two terms drop out. And I take a partial derivative with respect to z. I get xy coming from this term. These two terms drop out. And the derivative of natural log of z is 1 over z, and the constant goes away. And this is exactly the vector field I started with. So this is the correct potential function. All I have left now to do is to integrate. I need to know the endpoints of my curve. They were given to me. I wasn't given the specific curve. It doesn't matter. I have a conservative vector field. This integral is independent of path. As long as I know the endpoints, I don't need to know what the curve is. So now this integral, f dot dr over c, is the potential function at 1, 2 e squared minus the potential function at 0, 0, 1. So it's just a matter of plugging numbers in and working it out. So I plug in 1, 2 e squared into my potential function. I get 1 times 2 times e squared plus 1 squared minus 2 cubed plus the natural log of e squared minus 0 times 1, because I'm plugging in 0, 0, 1, plus 0 squared minus 0 cubed plus the natural log of 1. Now, all of these terms here end up being 0 because the natural log of 1 is 0. So there's nothing going on there. What's going on here? I just get 2e squared. That's 1. 2 cubed is 8. Natural log of e squared is just 2. The natural log and e cancel, and I'm left with a 2. So then my answer is 2e squared minus 5. So you can see a lot more work is involved when you have a three-dimensional vector field. So make sure you find some of these problems to do in practice and get the hang of finding these potential functions and evaluating these integrals. And that's it for section 16.3.